Okay, so first, I'm not going to be here on Monday. I'm going out of town. Um, and so the assignment I give you today will be due on Wednesday. Um, and we haven't gotten to any homework yet in this new stuff, so we're still just working through. Um, so remember, we're working on stresses and beams. Um, and the idea of this using the superposition principle is that the total stress tensor at a point in a beam is the stress tensor due to internal tension plus the stress tensor due to bending moment plus the stress tensor due to shear force plus the stress tensor due to internal torque. And we have talked about this one, and we have two to go. One thing I want to say about so the stresses due to tension and bending moment. So let's say we have this beam, and let's say that at this location here, say that we're looking at this part of the beam. Okay, let's say that we have an internal tension T and a bending moment M, like this. Okay, so say that they're in these directions. Okay, let's think about what the profile of stresses look like as you go from top to bottom along this cross section. Okay, so first let's think about the stress due to tension compression. Well, I guess we'll just think of tension. So I'm on the y-axis, I'm going to put my XX stress, okay? And on the x-axis, let's say that this is the midpoint. And let's say that this is the bottom of the beam. And this is the top. Okay. So how does the XX normal stress vary as you go from the bottom of to the top due to tension compression? With tension compression, so it's important. I think understanding these graphs is important. They're simple graphs, but you should understand what I'm getting at here. There's no difference due to tension compression as you go from the top to the bottom. The stress is the same everywhere along that cross section. So this would look like this. Okay, so there's no change. For a given internal tension or compression, the XX normal stress and the stress tensor due to tension are the same anywhere along the cross section. Now let's think about how it works for bending moment. So this is now the stress due to bending moment. And again, remember, it's only the XX stress that is non-zero due to bending. And again, I'm going to say that this is the bottom of the cross section. This is the midpoint of the cross section. And this is the top of the cross section. Okay, so what happens to the XX stress as you move around the cross section? Well, when you're on the neutral axis, what's the XX normal stress due to bending? Someone shout out a number. Here are the only numbers that anyone will ever ask you for in front of a class. -1, 0, 1, E, or pi. So you got a 20% chance to get this right. What's the value of the stress at the neutral axis due to bending? 0, that's right. The way that I've drawn this bending moment, it's, you can see it's flexing up like a smile, So the top is going to be in compression and the bottom is going to be in tension. And so this is going to go from, so it's going to be in compression down here. And then that line is going to continue like this, and it's going to be in tension here. And that's just a line. If the bending moment was negative, if your bending moment was negative, this would be opposite, and you would have tension near the bottom of the cross section and compression near the top. Okay, so, oh my gosh, am I going to keep getting these? How do I shut this off? So yeah, just remember that when you're dealing with the stresses due to tension and compression, it doesn't matter where you are in the cross section. The answer is the same. When you're dealing with bending moment, it does matter where you are on the cross section. It comes into it through that y value in the formula -my/I. Okay. Oh my God, she is now going to send 15 consecutive invitations to meetings. You can all see when my meeting times are. So don't knock on my door during the following times. So now we're going to talk about stress due to shear force. So let's think about, I'm going to try to draw a semi-careful picture of a beam. And somewhere inside this beam, we're doing an internal loads calculation and calculating the stresses. So let's say that it's there. And we want to evaluate what's happening to little stress cubes so like think of this as a row of stress cubes lined up on the face where we're calculating these internal loads. Okay, so just all in a row. It's a whole bunch of stress cubes. Okay. The shear force acting on this plane is a force vector like this. I'm trying to make it look so nice. Okay, so that is a shear force. Okay. And notice that our coordinate system is like, it's the same way it always is. X that way, Y that way, Z that way. Okay, so if you think of this as a stress cube, what's the corresponding stress element on those stress cubes created by that shear force? Think of each one of those as a stress cube.
Primary stress and
Well, so first of all, think of like what face of the cube is it? Is it the
negative y.
It's in the negative y direction, that's right. And then, so that's the direction of it. And what face of one of these cubes is it acting on?
The positive x.
Positive x. Yep. So if you think about it that way, it makes perfect sense that the stress due to a shear force is an xy shear stress. Okay, it's on the x face, and it's actually in the negative y. So a positive shear force produces a negative xy shear stress. Okay. So if you think of the green cubes as stress cubes, a positive shear force causes a negative tau xy shear stress. Okay, so now all we have to do is figure out what the value of that stress is. First, we have to talk about beam requirements. For internal tension and compression, bear requirements. Beam requirement. So for internal tension and compression, what beam requirements were there? That's right, there were none. Good job, everybody. For internal bending moment, there were 3 beam requirements. Anyone remember what those are?
Oh.
What? Prismatic. Yes, prismatic. Straight. And symmetric about the y-axis. Okay, so more restrictive on what we can use with that bending moment formula. For shear force, it's the most restrictive so far. In fact, it's so restrictive that I'm not even going to give you like a category of things. I'm just going to tell you the 2 cases that we can deal with. And that's really all we can. So this is the most restrictive so far. We can only do calculations for so there are 2 possible things. The first one is rectangular cross sections. And even that isn't enough. This also only works when the height is greater than the base. Or the only other places where our calculations are going to work are for circular cross sections And in this case, and then only along the neutral axis. Okay, so if you have a rectangular cross section with the height greater than the base, you can calculate the stress due to shear force anywhere along the cross section. So that's good. And another thing that's good is well, this won't let us do every kind of rectangular cross section, but remember, because of the moment of inertia, it's pretty common that we're going to have the height bigger than the base, because that resists bending more effectively. So this is okay. Like for rectangular cross sections, this is helpful. For circular cross sections, we can never do the whole cross section. All we can do is calculate the stress due to the shear force along the neutral axis of the cross section. So is that even useful? Like, do we care about that? Well, there's one thing that makes that a little more palatable, and that is that the biggest stress due to shear force happens along the neutral axis. Okay, so I'll say at least that's where the greatest stress happens. Okay. So if we want to do calculations for everywhere along the cross section now, throwing in tension compression, throwing in bending moment, and throwing in shear force, the only option we have that can deal with all of those is a rectangular cross section that's a tall rectangular cross section. Okay. Okay, and now let me graph out, before I give you the formula, the stress due to shear force. And I'm going to go back to this diagram, and I'm going to assume we have a positive shear force V. Okay. So what can we say about the XY shear stress as we go from the top to the bottom of the cross section? You haven't seen the formula, so you don't have any prayer of guessing this, but I'm going to show you this first, and then I'll give you the formula. So this is going to be our tau XY. And this is going to be the bottom. This is going to be the midpoint. And this is going to be the top. Okay, well, I said for a circular cross section, the biggest stress due to shear force happens at the midpoint. So maybe we would expect that to be the biggest value. Remember, a positive shear force corresponds to a negative shear stress. So our sort of maximum absolute value is going to be there. And in this case, it's not going to be linear. It's going to be like quadratic. Ay, that's horrible. Let me try that one more time. Okay. So it'll look something like that. So your biggest stress due to shear force is at the neutral axis. And notice that that's the opposite of the effect with the bending moment. With the bending moment, the biggest absolute values are at the top and the bottom. With shear force, it's right at the middle, and at the top and the bottom, it's 0. Okay. And the formula is So tau xy due to shear force is equal to negative v. So the negative is that effect where where a positive shear force corresponds to a negative shear stress, times q, and that's something I'm going to have to tell you what it means, divided by the area moment of inertia times b. Okay, so this thing is tau xy due to shear force. And this is the area moment of inertia. We already know what that means. This B is the width of the beam, the base of the beam, at the height of your calculation. And then this Q is the one thing we still need to define. Okay. And so here's the definition of Q. And I'm sure it has a mathematical name in terms of like it's a first moment technically of something, but I don't know what it is. I just call it Q. But so let's imagine that this is like an arbitrary cross section. And let's say that the neutral axis of this cross section is here. How would you calculate where the neutral axis is? Like what defines where the neutral axis is? You remember? Centroid. Yeah, it goes through the centroid. And let's say that this black line is, well, let me do green. Let's say this is where we want to calculate, this is our line of interest. And so this is where we want to calculate our tau xy. Okay. Well, calculate the area above that line of interest. Okay. And then calculate the centroid of that area, of that shaded area, the centroid of all of the stuff above the line of interest. So where would that be? Like here somewhere? And this green is the area A. Okay. And now calculate the distance from the neutral axis to the centroid of that area A and call this D. And then Q is defined as that area A times that distance D.
So it's from the center of the area under the green line?
So choose a line where you want to calculate it. Consider all of the material above that line. Okay. and calculate the area of all that material. Calculate the centroid of all that material above the line, and then multiply the area times the distance to that centroid. And notice this is always positive because that's a distance and an area. One sort of interesting factoid that you can prove about this. So notice you always get the exact same answer using the area below your line of interest. So you can do it that way too. It might be helpful in some cases where your line of interest is below the neutral axis. It seems a little surprising when you look at it at first, but it basically just comes down to some heights canceling out. But what that means is, so say this is your line of interest. Say you unshade that green up there and you shade everything below. Okay. Yeah, all of the stuff that's white is now shaded green. And now you find the centroid of that. Well, it's going to be somewhere below the neutral axis because we've removed some from the top. So it'll be, say, here or something. And then take the distance from the neutral axis to that centroid of that new shape, and you'll get the exact same number as what I drew there. Okay. Okay, so let's do an example. So now we have the ability to do calculations of stresses and beams for anything that doesn't have torques. Okay, torques about the x-axis. So now we can do lots of beam problems. So let's say that we have a beam like this. With a roller in the middle. And let's say that the mass of this beam is 30 kilograms. Let's say it has a length of 3 meters. And let's say that in between the roller and the pin joint, we have a force applied downwards of 2,000 newtons. And we're going to want to calculate the stress at the midpoint between, so all these things are just midpoints, midpoint between the 2,000 Newton force and the pin joint. Okay. And let's say we want to do it, so the cross section, let's say it has a height of 0.04 meters and a width of 0.2 meters. The neutral axis goes through the centroid, so it's there.
That's look from what view?
This is a cross section, so this is like looking down the end of it.
From the side.
The one on the left is from the side, And then this one would be like looking like this.
So the red line shouldn't be vertical. But
Oh, those red lines are not the same thing.
oh, they're not.
No. So this one is just telling you where the neutral axis is because I'm about to give our line of interest. And my line of interest is going to be um, at the midpoint between the neutral axis and the bottom. Okay. And that should be everything we need. Anybody have any questions about this? We're gonna calculate the total stress tensor.
The other red line is the cross section.
The one on the left. That is so. We are going to be calculating stress tensors that are on this x value of the beam at this point on the beam and along this line on the beam. Okay.
Or like
Yeah, so this specifies a cross section. And then in the cross section, everything along this line will have the same stress, but that's what we're going to calculate those points. So we're going to calculate sigma for the line of interest at the red cross section. Okay, the first thing we have to do is calculate the internal loads at the line of interest. And before we can do that, we have to calculate the external loads. So at the midpoint, this thing is 30 kilograms, so that's 294.3 newtons acting at the midpoint of the beam. And then we have the 2000 acting here. And then we have an RA here. Oh, let me put something else in here. Let's put this guy in too. Let's say this is 5,000.
that's just tension.
Yeah, so that's just going to give us a tension value, an internal tension value. And we'll call this RB. Okay?
How did you figure out the 294.8?
That is 30 kilograms times 9.81.
Why did you put it in the other?
Because once you choose your body to isolate, the weight always acts, if you're going to treat the weight as a point force, it always acts at the center of mass of your chosen body. It's really a distributed load, but as soon as you choose the body to isolate, you can replace your distributed load with an equipolant point force acting at the centroid. Okay, so I guess I'll put my about point here for this. Newton's second law says negative 5,000, 0, plus 0, negative 294.3, plus 0 RA, plus 0, negative 2,000, plus RBX, RBY is equal to zeros. So we have RBX is equal to positive 5,000. And RBY is equal to negative RA plus 2294.3. And then we'll go to the moment equation. The moment arm for the 2000, the whole thing is 3, so halfway is 1.5, halfway again is 0.75. So we have plus or minus 0.75 times 2000. Would that make it rotate clockwise or counterclockwise around the red dot?
So it's a positive moment.
Yep, counterclockwise, positive. And then we'll go to RA and the weight. That's a moment arm of 1.5.
What
What?
what is it the 2000 counterclockwise if it's going down?
Well, just think about, so the rotation happens about the red dot that we chose as the
Oh,
about
the red
point.
dot.
Yeah.
I was thinking of the center.
Whatever you choose as the about point, that's where you have to imagine it going. So 1.5 times 294.3. And would that weight force make it rotate clockwise or counterclockwise?
It'd be going clockwise if it's the RA.
The 294 would make it go counterclockwise. And then the RA would make it rotate clockwise. So 1.5 RA. This time we want negative. The 5,000 doesn't produce any moment. And so this is all just equal to 0. And so we get RA is equal to so I got positive 1294.3. And so that says that RB, if I plug that in up here for RBY, we got 5,000 for X. And for Y, we got 2294.3 minus 1294.3, so 1,000. Any questions about that?
Are we always gonna assume that we are like in statics?
Yes. Yes, in this class, we will never have a time where we don't assume it's static.
Okay. So we're never gonna set up equal to mass time acceleration. Right?
Exactly. Okay, so now we have to make our cut. And so, since we're trying to do this just at a specific point, I'm just going to make this cut right from the start. There's no reason to calculate everything in terms of X. So for my cut, we have a beam like this. And let's see, we have our RA of 1294.3. And then we have our 2,000 down. And we have our 5,000 this way. And then we have our weight force that we can treat as a point force at the midpoint. But I'm going to first draw it as a distributed load. We'll calculate what that is in a second. And then my internal loads are T, V, and M. There's no fancy T here. And for the distributed load, yep.
The distributed load is the weight?
The distributed load is the weight. That's right. So remember that since I'm doing a cut, it's not the full weight of 30 kilograms here. It's only, I guess it would have been easy to calculate. It was just 3/4 of 30 kilograms times 9.81, but I'm doing it in 2 steps. Okay, so we have, this whole thing is 3 meters. The weight is 294.3 for the whole thing. So take the weight and divide it by 30. And divided by 3 because the length is 3. And you get 98.1 newtons per meter for the distributed load.
So the weight is like the length of the beam, all of it, or?
All of it. So all the way from the left end to the pin. So the length of ours is, so now we have to figure that out. Let's calculate these lengths. So this is 1.5. This one is 2.25. And then to the end is, I guess, 2.25 plus 0.375. So this is 2.625. Anyone have any disagreements about any of this?
I just had a question about the weight. How did you put it down?
I took the total weight of the beam and divided by the length of the beam. So the total weight was 294.3. The mass was 3. So 294.3 divided by 3 gives you 98.1.
So we don't divide it by we divide it by 3, not 2.625?
Well, yeah, if you're dividing the total, I mean, what that distributed load is it's a weight of 294.3. You're trying to figure out how much weight per meter. So the 294.3 is the weight of all 3 meters. So you have to divide by all 3 meters. Yep.
How did you get the last measures?
The what?
Those are 2.675.
That was 2.25 plus half of 0.75.
Okay.
These are all just halves. So it's 1.5 from the left to the roller. Half of 0.75, half of 1.5 to get from the roller to here. So now we're at 2.25. Half of 0.75 to get from here to here. So I think that's what it is. And now I'm going to calculate for that distributed load. I want to represent that as a point force. It has a length of 2.625, a height of 98.1, and so the centroid is half of 2.625, which is 1.3125. And the area is 257.51.
Are we giving the height or is it the same as the weight?
So the height of that distributed load is the 98.1. Okay. Yeah. All right, so now I'm going to redraw this free body diagram with that weight represented as a point force. So we have the 5,000 here. We have the 1294.3 here. We have the 2,000 here. We have the weight force here, and that is 257.51. And then we have the internal loads. And the distances, we're going to need this for the moments. This one is 1.3125. This one is 1.5. This one is 2.25. And this one is 2.625. And we're going to calculate our moments about this, like we always do with cuts.
Then why do you choose the right side up above?
What?
Why do you choose the right side for the, like if you go up
Mhm.
when you first calculate the external loads, is there a reason you chose the right side versus the left?
I just chose it so that RB wouldn't be in the
Oh,
moments.
so you have to calculate.
Yeah. All right. So Newton's second law. Negative 5,000 0 plus 0 negative 257.51 plus 0 1294.3 plus 0 negative 2,000 plus T negative V is equal to zeros. And so T is equal to 5,000. And V is equal to negative 963.21. And then we'll do the moment equation. So the moment arm for the 257.51 is 1.3125. The force is 257.51. Would that force make it rotate clockwise or counterclockwise? Clockwise, so we want the negative. And then we have the moment arm of 1.5 times the force of 1294.3. Would that make it rotate clockwise or counterclockwise? Counter. And then we have the moment arm of 2.25 times a force of 2,000. Would that make it rotate clockwise or counterclockwise? Right? And then we have plus m minus Vx, and actually we know what x is. So this V is times 2.625. And V is equal to negative 963.21. So M is equal to that's a positive. Yeah, 963.21 times 2. And I got 368.11. Okay, anybody have any questions about that? Okay, so finally, we haven't done anything but statics yet, but now finally we're at deform stuff. Now we can calculate the stress tensor. So first I'm going to do tension compression, the stress due to tension compression. So sigma xx is equal to 5,000 divided by the cross-sectional area. So I'll go way back up here to the cross-section. That's 0.04. This should have been 0.02, not 0.2. So 0.04 times 0.02. So that is 6.25 times 10 to the 6. And so the stress tensor due to tension compression is 6.25 times 10 to the 6, and then zeros everywhere else. I didn't consider where on the cross section we're looking at this. Why is that? Because it doesn't matter because of this graph right here. Stress due to tension is flat across the whole cross section. But it will matter for the other two. Okay, so now we're going to do the stress tensor due to the bending moment. Well, sigma xx is equal to negative my over I. I is equal to 1/12 times the base, which is 0.02, times the height cubed, so 0.04 cubed, so that is 1.0667 times 10 to the minus 7. And this is meters to the fourth. Now we need the y for this equation. What's the y value for the black line, the line of interest here?
Negative 0.02.
So the whole, yeah, you're thinking about it right. The whole height is 0.04. So half of that is 0.02, so negative 0.01. The key thing is if it's below the neutral axis, you need that negative sign. Okay, so remember that this is signed. So y here is equal to negative 0.01. And so sigma xx is equal to, I get my bending moment, 368.11. So 368.11 times negative 0.01 divided by 1. Thank you. Divided by 1.0667 times 10 to the minus 7. And you get 3.451 times 10 to the 7 pascals.
Is that formula for the inertia different from the others?
Is that what?
The formula for the inertia?
Nope, that's the only one we've used in this class. Yep. We will have another capital I with torque, but it'll be I sub P. So, okay, and so the stress tensor due to the bending moment then is I'll write it as 34.51 times 10 to the 6, and then zeros everywhere else. You can see that that bending moment contribution is quite a bit bigger than the contribution from tension compression in this case. Does it make sense, intuitive sense, that this is a positive stress? So does it make sense that due to bending, this is in tension? Well, we have a positive bending moment at that point. So this thing is bending up like a smile. Okay, so things on the bottom are getting stretched. Can you visualize that? Okay, so yes, this makes sense. And now we're to what we did today, the shear force. And tau xy is equal to negative v times q over ib. We already have I. B is, for a rectangular shape, it's the same at any height. So this is just 0.02, just the width. And now we can think about that Q. I think this is a case where it probably is a little easier to imagine calculating Q with the area below our line of interest. So I'm going to draw this cross section like this. Here's the neutral axis. Here's our line of interest. Here's our area A. Here's the centroid of our area A. And this is our distance D. Okay, so for the area, this height here is 0.01. So the area is 0.01 times 0.02. And so that is 2 times 10 to the minus 4 meters squared. You with me on that?
How did you know that?
The what? Well, the height of the whole thing is 0.04. So half of that is 0.02. And this is half of that half, so 0.01. Yeah, the width of 0.02 is given in the statement of the problem. Bless you. Okay, now where's that centroid? So that centroid, to get to that centroid, you have to go a distance of 0.01 to get here, and then 0.005 to get to the middle of this. So that's 0.015. And unlike y, this is a distance, so it's not signed. We're going to keep that positive. Okay? So our D is 0.015 meters. And so our Q is 0.015 times 2 times 10 to the minus 4 and you get 3.0 times 10 to the minus 6 meters to the third.
Right, so the area is the area of the group, right?
Right. And our I we got before was 1.0667 times 10 to the minus 7, I think. Yes. And this is meters to the fourth. And our shear force was negative 963.21. That's newtons. And so tau xy is equal to negative of negative 963.21 times 3.0 times 10 to the minus 6 divided by 1.0667 times 10 to the minus 7 times 0.00, no, too many O's, 0.02. And we get a value of 963.21. 1.35 times 10 to the 6. And so the stress tensor due to shear force is 0, 1.35 times 10 to the 6, 0, 1.35 times 10 to the 6, and zeros everywhere else. Any questions about that? And so finally, our total stress tensor is just the sum of these three. So the one due to tension, plus the one due to bending moment, plus the one due to shear force. And that is 40.76, 1.35, 0, 1.35, 0, 0, 0, 0, 0. And so now if this was a brittle material or there was some brittle connection point at this location, supposedly that's why you were interested in this one location. Now you could calculate the principal stresses, use that to calculate the maximum shear stress, and see if your maximum shear stress exceeded some limit. Question?
Yeah, wouldn't it be megapascals?
Yes, thank you. Thank you. And you could also put this in a Voigt form and calculate the Voigt strain if you knew the material properties.
And then all these are like calculated from like the green line.
In the original pictures?
Yeah, like
or the Q picture?
The original picture where the line of interest. This is calculated from the line of interest, right?
Yes. I guess it's black in this drawing, green in a different one. Right.
Okay. And it goes all the way through the beam. It's not just one section, or is it just the section?
It is just the cross section. It's just the red cross section, and every point along that line has the same answer.
Okay.
So we really calculated the stress at a line of points, not at a single point.
Okay.
But it only holds at this cross section here because that's where we did our cut. Any other questions right now? Okay, so I'll give you an assignment doing this kind of stuff, and it'll be due next Wednesday. And try to do it. But if you get stuck, I'd be happy to do problems that you have questions about on Wednesday. Goodbye. Goodbye, Minnesota. So long, Stinktown.